So before we go any further, I suppose a quick proof is in order, and the proof is about as straightforward as the statement itself. I've got the original pigeonhole principle on the first sentence here. That's just restating it. And what I'm going to do is I'm going to show this by contradiction, right? So assume that we have n items, and then they have to be sorted into m groups, and this is the contradiction part, that no group will have more than one item. All right, we need to see that this leads to a contradiction. So let's have our M groups, and I'm going to start putting my items into them. And remember, I need to do this in such a way that no group has more than one. So once I put an item in a group, I can't put one in there again, or it's going to violate that constraint. So we're going to keep going, and by the time we get to this last one, now we've allocated uh, m of the items, but because there are n of them, and n is strictly greater than m, there is at least one object, one item left over. So wherever I put it, it doesn't matter which one I pick because they're all full at this point, wherever I put it, that's going to create a group that does have more than one item. Contradicts my assumption. Therefore, the original assumption must be false. Therefore, the pigeonhole principle is true. So I've listed this statement here that a function from one finite set to a smaller set cannot be one-to-one as a theorem. I've listed this as a theorem, but it's often actually given as the statement of the pigeonhole principle. So you'll see the two used interchangeably. So to see that this is true, let f be a function from a to b. F is a function from a to b, and assume that the cardinality, the size of a is n, and the size of b is m. Now, since b is the smaller set, right, we have n is greater than m, since b is strictly smaller than a. So using the terminology of the pigeonhole principle, the elements of A are the items, and the elements of B are the containers. Now, since the requirements of the principle are met, right, we can conclude that there must be at least one element of B that has more than one item of A assigned to it, which means that the function, in fact, is not one-to-one. So in the next lecture, we're going to look at some examples, right? We'll look at some situations where we can use this pigeonhole principle to answer some specific questions.